posso apontar aqui. Posso apontar. Isso aqui é mais lerdo. Esse aqui não é to let it fresh.
Okay, I think it's time. It's time to start. Just a minute before, just like to check whether, let me see here. Nalamala Kiran. Nalamala Kiran is here. Does anybody know her? Or him? Okay, there's one missing person. Ramon Moreira Pérez. Ramon Moreira Pérez, not here. Renato Murbach. Does anybody know him? You know him? He has been here. This Renato guy has been here. Student of Marcos. But you have seen here yesterday or today? Yeah, okay. Ramon is here. He's been here. Ramon and Renato have been here. Okay. Okay, so we are coming now to the final session of today, and then please get your delicacies to the table downstairs, and let's see what kind of surprises we are going to find. For me, already, I have been living here for a few years, and for the first time, I had this jabuticaba juice, which was fantastic. One of my favorite fruits. I was not aware that we could make a juice, a nice juice out of the jabuticaba.
Only liqueur.
Huh?
Liqueur you knew.
Liqueur, I'm sure. Liqueur, I'm familiar with the liqueur of jabuticaba. That was the juice. Anyway, Eduardo Bellini is a professor here at the University of São Paulo in the Material Science Department at Campus 2. You're going to visit his lab.
On Saturday.
Saturday morning, and he has been working for many years with glass ceramics. So thank you so much, Eduardo, and let's see what you have to tell us.
Thank you. Hello, everybody. It's a pleasure for me to talk to you, and I try to make it simple, okay, for general audience that maybe some of you already know about what I'm going to tell here, but some of you, I think, it's not used to the subject. And thank you, Edgar, for the description, so I can just skip this. This is our university. We are here now. Just now we are, let me find here. I try to, here, in this position here. This is area 1 of our University of São Paulo, in São Carlos. we have a second area about 3 kilometers far from here, and our materials engineering department is here. Some of you are going to have chance to visit us. This is the face of our institute, our department, but now we have many more. The trees have been growing and it's a little bit more beautiful now. Well, I was asked to talk about glass ceramics. Glass ceramics are polycrystalline ceramics obtained by the controlled crystallization of glass. We get used to this definition. So glass must be obtained first, formed by some process, pressing, blowing, and so on, and converted into a polycrystalline material by a proper thermal treatment. And the thermal treatment has to be managed to produce a microstructure that is able to get us some nice properties. It started with Stuckey at Corning, United States in the 50s. He accidentally overheated glass in the system lithium and silicate with silver particles inside to trying to obtain a photosensitive glass like this one here. This is a kind of permanent photography. At that time, they managed to produce that. Actually, it was Stuckey who invented that in 1937, also at Corning, and he was trying to improve the properties of this glass. In the beginning, it was in the system sodium oxide, silicon oxide, and to improve the chemical resistance of this glass, he changed it to the lithium silicate system to get a better chemical resistance with gold nanoparticles. So this was the glass that he forgot in the furnace, and in the next day, he was frightened when he found the furnace at 900 Celsius degree, much higher than the temperature he he planned to let the furnace. And in a hurry, tried to pick the fragment. He thought that the furnace was destroyed, but actually he was able to get the white piece inside the furnace, let it drop on the ground, and the sound, it sounded like a metal. And that informed him that was interesting, because it didn't break when he dropped it, and he was smart to understand that piece of glass had crystallized. But he remembered that Hummel, more or less in the same time, had described a beta-spodumene composition that had near zero thermal expansion coefficient. So he tried to bring that system, the fact that he had just discovered, but when he tried with silver, it didn't work properly. And he knew that this opal glass used in thermometers, at that time, this opal was produced by titania. And so he tried titania, and it worked perfectly. And he was able to produce then a very nice glass ceramic by the first time, and developed Corning to get a product for commercializing as a pan for cooking, but also as a nose for missiles. That drives a lot of things, actually. And you see, since then, that has been produced this 750 million pieces of these products, not only at Corning, but in other companies too. It was a big success. And this material, because it has a very small thermal shock coefficient, it doesn't break if you bring it from the oven to the surface of the kitchen where you wash or serve, or if it comes from the table directly to the fire, it doesn't break. It's very interesting material. Well, this gives you some sign of what's interesting when you work scientifically or looking for some technological development. Stuckey was lucky, nobody can deny, but actually he was also careful to observe what was the new result that he observed. He had solid technical knowledge to figure out what was the best to do, and he was up to date with the literature and clever enough to guide the invention into a higher impact product. It was not he didn't announce it very in the beginning of the discovery. It took 10 years to this product appear in the market. Well, this history is well documented. If you are curious about the details, you can find the literature that will be available for you. And I will follow more or less what's in this book from Holland and Biel. I suggest, if you want a fast review about glass ceramics, you can read the Zanotos review. It's not so up-to-date anymore, so it has to write a new one. But I think if you have time to dedicate to this, this book is very nice. Okay? Well, what's glass ceramic exactly? Sometimes we see in the literature the term, if you put in the Google academics glass ceramic, you can maybe you'll find glass matrix composites or ceramic in a glass matrix composite. And there is some confusion about the term, so we have to care. For example, here we have a ceramic abrasive bonded with glass. Here we have alumina grains or particles, very sharp, and that is glued with some glass. So it's a glass ceramic composite, but it's not a glass ceramic that we are dealing with here in this school. That one is obtained by the crystallization of glass, and this is not. The glass here doesn't crystallize. I'm sorry, there is some problem here with the format, but there is also crystallization that is obtained when you're trying to make a glass, but by some problem, just some process problem, the glass got crystallized as a defect. We called this defect as devitrification, And this is not controlled crystallization. Actually, we have to dispose the products that have this kind of defect. They have to be separated from what you're going to sell. And the name of this is devitrification, to separate it from crystallization by a controlled way to obtain glass ceramics. Okay? So it's not all the crystallization of glass that produces a glass ceramic. And recently, a team of very researchers that are very used to the subject, Deubner, we have here Ralph Miller that just talked to you, and Professor Zanotto and others, they came into this definition. Glass ceramics are inorganic, non-metallic materials prepared by controlled crystallization of glasses via different processing methods. They contain at least one type of functional crystalline phase and a residual glass. The volume fraction crystallized may vary from ppm to almost 100%. So it's a very abrangent definition, but I think in general, for the ones that are already used to it, it's just enough to say that if you get some polycrystalline materials by the controlled crystallization of a glass, and you find that this material has some interesting properties, we call this glass ceramic. So to obtain a glass ceramic, we have to achieve two fundamental conditions. We have first to get a glass, melting some raw materials above the melting point, the liquids, and then fast cooling it below Tg to obtain a glass. And this glass is after reheated above the glass transition and let time enough to crystallize, and then we have a glass ceramic if the microstructure is regular and with good properties. In this process, a microstructure of interest is sought. It is expected in general, mostly, to look for fine submicrometric crystals regularly dispersed through the volume, and a residual glass that is not easily saw here in this picture. This is the Stucky glass ceramic, based in beta spodumene solid solution. And you see here the grains are very near to each other and more or less 1 micrometer in diameter. This glass ceramic is not transparent. This is white. To have it, to get it transparent, we have to have even smaller grains to don't spread the light. Okay, the grains must be smaller than the wavelength of the visual light, the visible light. But sometimes we also have coarsely crystallized glass, and they are also interesting and find nice applications. For example, here we have a piece more or less this size. This is a sample where we can see the crystals by naked eye, and that mimics the granites or marbles, natural rocks for buildings. So there's a lot of possibilities possible a lot of possibilities using this process. In general, there are two main processes, routes that we could follow to obtain a glass ceramic. The glass can be formed in the volume. The glass can be crystallized in the volume by a proper design of composition and addition of nucleation agents. But also we can use a glass powder form using the traditional methods found in the ceramic industry, and then treat it for sintering and crystallization that Ralph had said a lot in the last talk. Well, going a little bit into more details, glass ceramics by volume crystallization can be produced by melting the raw materials, and the raw materials are the components that we need to form a glass. And in most cases, we have to add nucleation agents. And here is the step that we need to homogenize very well the melt and the glass. Only some compositions can crystallize in the bulk without the addition of nucleation agents, lithium disilicate, barium silicate, and so on. But there only a few of them are able to crystallize in the volume without the use of nucleation agents. That kind of crystallization, that kind of nucleation are called homogeneous nucleation, but all the systems, even that nucleate in the volume, also crystallizes, also nucleate heterogeneously on the surface. And so to get a regular and fine polycrystalline microstructure, in the industry, we have to add nucleation agents. And that glass is formed by somehow, again, pressing or blowing or centrifugating. And then after we obtain a glass product, it is reheated at a convenient temperature for crystallization. And after cooling, we get this glass ceramic. Volumetric crystallization has more or less this appearance. First, we have a step of nucleation or activation of nucleation sites, and where the crystals will grow and stop growing when they achieve the neighbor. Okay? And we have this kind of microstructure here, where this was chemically attacked, and we see the crystals, and in the bottom of the surface, we see the residual glass still there. Okay? The advantages of producing glass ceramics by the volume crystallization, we are able to deal with complex composition. That's interesting because we can put a lot of components inside, and using a lot of components enable us to design the properties of the glass for some application, and also to match different properties, only changing the glass composition, because the properties of a glass normally change smoothly with the composition, like thermoexpansion coefficient, modulus, elastic modulus, or hardness, and so on, and to match different properties. That's possible with a glass, not easily achieved using the ceramic process, the traditional ceramic process from the raw material. And that also allows us to assimilate in the composition many inorganic wastes. That's why you find in the literature a lot of papers, people trying to reuse wastes to produce a glass and a glass ceramic, trying to solve the problem of waste in several activities. And as we are able to control the properties using this complexity, this is a system that we could work for optimizing using machine learning prospection. The production, industrial production of glasses needed first before obtaining a glass ceramic can be very, very high efficient in forming. It produces a lot. The crystal number and size and the crystallized fraction can be controlled by heat treatment, by the composition, by the addition of nucleation agents. We can design the microstructure. Make it properly, it's possible to obtain zero porosity. That's very, very hard using the traditional ceramic process. And we can produce complex shapes because we form from the liquid state, and that allows us to produce very, very different shapes. Disadvantages. We need to form a book article, and so the system the composition has to be a good glass former. Otherwise, it will crystallize, not in a controlled fashion, and destroy the process. So we have to find the compositions that are able to form a glass in a bulky product. The forming at high temperature is expensive. It needs metallic molds that are very expensive. And the industrial apparatus is expensive. And often, we need to add nucleation agents. And that's not easy to find for every composition. We know nucleation agents for some systems that work very nicely, but it's not general. And we don't know how to look for a special nucleation agent for every composition that we are dealing with. So this is sometimes a limitation of the process. We have a good idea, we find the glass, we find a crystalline phase that could give us some nice property, but we cannot make it crystallize in the bulk. It's quite difficult. Wow, it changed the format here. I'm sorry, that was not happening in my computer, that is happening here. Then, glass ceramic microstructure can be designed by controlling nucleation and crystal growth. For example, here on the left, there are many nuclei, so we spend more time in the nucleation step to achieve higher nucleation density, and then we heat again for crystal growth in a higher temperature, and then we crystallize all the glass, obtaining is very small crystals because they stop growing when they hit each other. Okay? But the same glass can be obtained in a different microstructure with a few nuclei, letting less time in the nucleation step. So as we have a larger distance between nuclei, the crystals can grow more, and we have a coarser microstructure. So we can manage to control the microstructure, the crystallized fraction, then the size of the crystals in the microstructure. That's not, in a way, that's not possible using the traditional method, ceramic method, by the powder technology. To give you some reference, if we make a DSC, or a thermal analysis characterization of a glass, in the heating we find the Tg as a changing in the baseline in the endothermic direction, and the glass can or not crystallize in the time of the thermal analysis. If it crystallizes, we see the crystallization peak, maybe another one, depends the composition, and then the melting. And the end point of the melting marks the liquidus, more or less. It's an estimate of the liquidus of this system. If we have a very good glass former, after Tg, we don't see crystallization and we don't see melting. It's only a flat line, horizontal line. This result can change very much depending on your sample. If you have the particles are coarse, the size of the particles are large, you have a broad peak. If you mill it, grind it into a finer powder, you have more surface to crystallize, and in general, the surface crystallization predominates, deviating the peak to lower temperatures. So you have to learn to study how to analyze these results, okay? And here in this, on the left, we have a graphic that shows you nucleation rate, the intensity of nucleation rate, and here on the right side, we have the intensity of crystal growth rate or speed, and more or less they overlap, as Zanot had said, and we have a peak of nucleation more or less nearby Tg. The maximum crystal growth rate is more or less nearby melting point. And that's why we can manage to nucleate without the effect of crystal growth and then increase the temperature for crystal growth without having more nuclei in the system. So that's why we can manage to change the microstructure in this kind of process. Not all the glasses have the same overlap. Some overlap more, others overlap less. So you have to map what's happening with your system to design the project, to design the thermal treatment and the microstructures. The controlled crystallization of glass has then led to the production of a wide range of materials, many that are very successful commercially, and with properties and applications that would be not possible using the traditional ceramic process by the powder technology. To give you some examples, we can see telescope mirrors. I'm going to show you a picture. Fracture-resistant dental prostheses, transparent cooking utensils resistant to thermal shock, tiles resembling natural rocks, such as marble and granites, and many, many other examples. Here you can see some of them. I think this generation doesn't know anymore what is this. It's impressive how things change fast. But this is the HD from the former computers made by glass ceramic. Because if the device heat, it doesn't change the dimensions to allow the memories that don't the computer don't make mistakes to find the information in the HD. We have this telescope mirrors here. Some of them are 8 meters in diameter. And how could you make a piece of ceramic of this size otherwise using this glass processing and crystallization? And here again, the dimension is very important because it's in the peak of a mountain in Chile, where during the day is very hot, during the night is very cold, and the temperature difference could make expansion and contraction of this mirror produce some optical aberration, and as this big piece of glass ceramic doesn't change dimension with temperature, so you have a more precise optical device. This one's maker from Corning is a kind of glass ceramic that can be machined as a metal, drilled, and machined, and so on, different pieces, different shapes and details, fine details that are not possible using any other ceramic material. You should, to use other ceramic materials, you should form into the shape and get it after heat treating or sintering, ready for using. But here you get a block and machine it in the shape you need. Dental materials that are very similar to the natural teeth. Pans for cookingware, tableware, precise pieces for devices, cooktop, and so on. This is some kind of glass ceramic you can make using this process. Here, just to focus in one system, we have a system that's similar to that Stuck invented, but this is the microstructure is let finer. It doesn't let the crystal grow above some size, so you have the crystals below the size of the crystals are below the wavelength of the visible light. That's why it's transparent. And there are a lot of concurrents in the market using more or less similar composition. And United States, German, Japan, and so on. And some applications besides the bowls, the pans, cooktop, telescope mirror, but also a fireplace window. If you have a fireplace window made by glass, it could be toughened glass. If you, by some bad luck, let the wine escape and achieve that, glass breaks immediately. And that doesn't break. It's much more safe. Doors that are fire safe, and so on. Okay? This is the kind of the mirror, one of the mirrors that they built, they produced it and managed. They produced it in Germany and transported it to Chile for assembling the telescope. This is one of our glass ceramic made by volumetric crystallization. It's in Portuguese, I'm sorry, but this is made from steelmaking slag that is wasted by the industry. And even today, they don't find much what to do with this waste. And after so many years, Edgar, I'm very impressed finding this is still shining. The surface is not attacked by moisture. It's there is the same as in the same day I prepared that in Lamave more than 20 years ago, maybe 30, no, between 25 and 30. Yeah, on Saturday I can show you this, okay? The ones that have the luck to visit us. The other route to prepare glass ceramic by sintering, you again have to mix the raw materials and prepare homogeneous glass. But the homogeneous glass, it doesn't need to be so homogeneous now, because you're going to mill, to grind it, or to frit into the water to get small fragments, and then you're gonna mill and adjust the size distribution, and you have to properly disperse the particles. Otherwise, when you press or form, you're gonna get porous, compact, that is difficult to. The porosity is difficult to remove after by sintering. Then you, by some way, have to form the powder and go to a step of sintering and crystallization to obtain the glass ceramic. The surface crystallization here is in the beginning of the process a problem that you have to control, because if it is too fast, it will limitate the viscous flow sintering and densification of the compact, and you're gonna get a porous glass ceramic. If you manage to first densify and then crystallize, you can achieve some nice products. Well, glass sintering and crystallization is more or less this. First, you have the viscous flow sintering of the glass above Tg, removing the best you can the porosity, and then surface crystallization from the particle surface, and the particle surface is everywhere in the bulk, so you have bulk crystallization from the surface of the particles. That's a way to get volume crystallized glass ceramic from glass particles. Here you see spherical glass particles with some crystals growing from the surface after they got sintered. And well, advantages, the same as before, because as we start from the glass, we can design the properties, changing the composition of the glass. But now the forming is easier because it can be achieved at room temperature. It can be at a high rate or not. So it's friendly to small production. If you are thinking to produce an electronic device or something smart that you had a good idea, and then you don't need to buy a glass industry to produce that. You can make it easily in the garage, in a small production. You can use nice process, tape casting for LTCC, 3D printing, all of these kind of things are possible. For processing, when you are processing, for example, porcelain, you have to mix quartz, feldspar, clay, different kind of clays. So when you mix that with water to produce a slurry, each of them have a different behavior in solution. And the dispersion is not easy. So you have a heterogeneous system. When you melt all the components into a glass, so you have one phase in the system to processing. That makes the process, the ceramic process, easier. No need for nucleation agents, because all the surfaces are now a place for nucleation. And instead of compositions, it's possible in the sense that the glass that you have to produce is not a bulky glass or a volumetric piece of glass. You can make small fragments, very fast cooling, for example, between cylinders, or pouring the glass in the water, so you have a much faster cooling, much higher cooling rate. And then you can get a glass from not very good glass formers that increase the range of compositions that you are able to use now. And disadvantages are porosity is very difficult to eliminate from this kind of process, or by surface crystallization, or by trapping of gases in the book, as Ralph had defined very well. And it's limited to glass compositions, the compositions that are able to form a glass, and also that could sinter before crystallizing. Otherwise, you could not densify using the viscous flow sinter. Yeah, you always are able to sinterize at higher temperature in the crystalline state by solid diffusion, solid state diffusion. But that breaks a little bit what's nice in the system that could be sintered at lower temperature than traditional ceramics. The kind of microstructure is more or less this. This is Neoparis, first produced in Japan. This is very well, very nicely densified. You cannot see here pores, and the crystals are needles from the surface. We see here some residual glass, but the system works very well. And this is a sample of our research. It's a diopside glass crystallized from the surface. In the middle, in the center of the particles, you see the residual glass. If you let in the furnace, the residual glass will decrease in amount, and you have more and more crystalline phase. But here you can see the pores that are appearing in the system, different kind of pores. I'm going to tell you more. These are trapped pores due to the surface crystallization, but as the density of the crystalline phase is very much higher than the glass phase, you have spherical pores inside each particle. This is difficult to avoid. If you're lucky to have the same density, you don't have this problem. But in general, the crystalline phase is denser than the glassy phase, and some some intensity of this problem you may face. This is the application of nail paris. Very nice tiling for architecture. And what's nice here is that they can change color, produce curved pieces of ceramic that are not possible using marble or granite. And also, as it is the porosity here is very near zero, and this material is very resistant to freezing in countries that have an intense winter. I'm sorry for what happened here. I was not expecting that formatting problem, but I think we can see here nail paris compared with marble, natural marble, and granite. The bending strength is much higher. The hardness compared to marble is higher, but granite is higher too. It's so high, as high. The thermal expansion coefficient is a little bit lower. It's good. Acid resistant, much lower than the others. Much more than compared with marble. Alkali resistance is, again, very low. The freezing and thaw resistance is the best. Water absorption, 0. And this diffuser reflection, it's the surface aspect is very high. It shines. That's why you have this effect here, this shining, this reflection, very high reflection here. Well, when exploring new glass ceramics, we primarily focus on the properties that we are more motivated to produce in the product that we are pursuing. For example, if we are trying to produce a bioglass ceramic, we have to have exceptional bioactivity and non-toxicity. For solid-state batteries, we have high ionic conductivity, for example, efficient electrolytes. For dental applications, we want high toughness, strength, and aesthetics. For cookware, we want to find thermal shock resistance, chemical resistance, zero porosity, to prevent the accumulation of organic material, and so on. In general, when we start in the laboratory, we are focusing in the application, and we're looking for these properties. But to get a glass ceramic, we face many other problems, many other properties that have to be managed to work, that sometimes we only will realize that it won't work after some 5 years PhD time, focusing in the thermal shock resistance, for example. For example, the thermal expansion coefficient of the phases present in the system have to be aligned to we don't have cracks in the system. They have to be compatible to avoid microcracking, and also the density of the present phases have to be managed to don't have the pores that appear when you have glass crystallizing in a confined residual glass. Okay, and problems with foaming and also problems with maybe you have a very dense and nice ceramic with the property that you need, but it's the chemical resistance of this ceramic is very poor. So there are a lot of other properties that you must manage to be successful in developing a glass ceramic product. Here again, some examples of our materials that we developed. These are from bottles, the glass waste from bottles, sintered and crystallized. Here, more crystallized than here. Here, after polishing, here it's the way it's obtained from the furnace. Here, after polishing this piece of glass ceramic. This is a nice piece, a big one. Unfortunately, we don't know where it is anymore. We lost it. Do you have one? The last one? Eu sou seu herdeiro. Okay. So, when you visit La Mave, ask Edgar to show this one to you. Okay. And here we have some examples of glass ceramics that are produced in La Mave, in Certev, for ear implants. These are for eye implants, for blind people, for aesthetic applications. The difference here is that it glues in the muscle. And I guess Oscar will give you this picture for them in his talk. You cannot recognize which one is the artificial one because it changes the direction when you move the direction you see. It's very interesting. And other applications, powders, a blanket of fibers. Some of them are glassy, the others are glass ceramics. And technical difficulties, as I said to you, if you have, like here, glass density much smaller than the density of the crystallized phase, you have the crystallization from the surface. Here, the crystallization from the surface was too fast, so we were not able to densify. Here we have the resin, so we have the porosity that the residual porosity due to not complete densification, but we also have the pores due to the difference of density of the present phases. So this is an issue. And also, if you have a thermal expansion coefficient very different from between the phases that are present in the microstructure, as at higher temperature, at the temperature the microstructure was produced, the phases are glued together. On the cooling path, they will crack. So you have to see cracking microstructure, cracking the microstructure that will destroy your mechanical properties. Here again, I got some examples of the guys that are here. Chico, Zanotto. You can see cracks propagating from the crystal. That's because the crystal contracts less than the glass matrix below TG. You have radial cracking. And here, cracking inside the particle that was crystallized on the surface, but due to the difference of thermal expansion coefficient, you have this issue. Well, that's it. These are some of my group. Most of them had left already, and most of them are not in the picture. I have to take up a new picture. I'm sorry, Anna. Luis. And thank you very much again for this opportunity to talk to you.
Okay, thank you very much, Edu, for your review talk. Anybody interested in glass ceramics or other crystallization problems? Henry and Masoud. Yeah. But it's on YouTube. You have to get the microphone and do it properly, please.
I'll be famous. Well, you just asked who's interested in all of that, and I just wanted to express that I'm interested in these things. So thanks for this nice, very visual talk. It's always nice to see. This is really something I like about the whole work with glass and crystallization. Sometimes you get really, really, really nice pictures. I don't have a particular question right now, actually. I think it was a very good overview. But I answered your question. I'm interested in that. I like it. I just wanted to express my support.
Your happiness by the talk.
Thank you very much. It's
Thank
always
you.
nice to have a positive comment, right?
Thank you. They're thinking on the seats.
Masoud is taking. And thank you very much for your presentation. It was fantabulous. Thank you. I have just one question. Why we need firstly make the glass and decrease the temperature below TG, and after that reheat it to over TG and stop somewhere there? Why we cannot make crystal glass during heating, during cooling, the cooling process, and stop somewhere there for some hours to make crystal glass?
One answer to this question is, for example, when you see this graphic here, here, in the cooling path, you are having fast growing with not many nuclei. So you're going to have a coarse microstructure. If you want to have a fine microstructure, you have to path very fast here and then start again, treating here to have a high density of nuclei in the bulk and let them grow just a little bit in the microstructure, okay? But maybe you're lucky enough to find a system that's well crystallizing to give you a microstructure enough for application from the cooling, on the cooling path, then it's okay.
Yeah, just to follow up on your question. Well, I guess in principle you could do this kind of cooling and simply stop slightly above TG, né?
Yeah.
But what might be a little bit difficult, the cooling, then you cannot produce a very nice shape in this way. Then the advantage of the glass to crystal transformation from the bulk glass is that you, by casting, you can produce a very nice shape, desired shape, and then you.
If it is too thick, it's difficult to control this. You have to cool. Of course, you're going to cool completely to room temperature. You're going to stop in a convenient level and then heat again.
And normally, then you have to kind of heat it under below TG a little bit to eliminate the tension in the glass, which would also be a problem in the glass ceramic. So for this reason, there's many good arguments for actually starting from the glasses at room temperature.
I agree. That's right.
But I have also a comment, and that is, so this carbon dioxide that we heard about in Ralph's talk a lot about, gas that produces the foam,
gassing.
the gassing, the foaming. Would this not also interfere with your annealing of the glass to do crystallization or nucleation or growth, or are these different temperatures? Do you observe this foaming at much higher temperatures?
When we when we are dealing with the powder, the glass powder, very often we see foaming. Especially when we are using the window glass or container glass, where the glass transition is very low, comparable 550 or so. At 700, it starts to soften and sinter. Maybe it's not enough to eliminate all the things that are able to produce gas, and it bubbles, it foam. Nicely, it can produce some nice products, very, very light, if you can control this. But many of us have observed this. But if you, for dioxide, for example, that the glass transition is not so low, I never observed it. It works very well. We are observing now that we are trying to make 3D printing, and the media for printing is a resin, organic resin. Then we have a lot of organic material that has to be the binding, that has to be eliminated before sintering. And so that's hard. 1% that from 1% is enough to get the sample black. And if you overheat it, it foam. It's difficult.
Thank you for your excellent talk. I have a practical question, or at least ask you for some advice. We have some lithium disilicate that we want to have very small crystals, but very high volume fraction. So we start doing some heat treatments, and after 12 days, just at nucleation, the nuclei has grown up to 3 microns or 2. So, but then we are at very low volume fraction, and the nuclei has grown, So should we do a higher heat treatment that there are nuclei that we don't see? And, or should we go down in temperature, let's say 20 degrees lower, then the nuclei won't grow up to 3 microns, but then we have more nuclei, or should we go to some phosphorus adding to increase the nucleation rate? I mean, what do you suggest? The question is, we want crystals of 3 microns, but after 12 days, we already have them because the nuclei has grown. Yes, lithium disilicate. Yes. Or perhaps there are nuclei that we are not seeing, and there are already nuclei that has grown. I mean,
did you check the temperature of your furnace? It's a source of error. This can be a source of error. We find 20, 30 degrees in a lab furnace easily. You have to make like Foking, using the most precise furnace that you cannot open. Use a tube to put the sample inside without opening. You see it drop in the
measure mechanical properties. So let me tell you something that I did not show in my talk. All those maximum temperatures of nucleation are incorrect. All of them, right? Elena, there is Elena. She discovered that. Thing is, below TG, you have these extremely long induction times. So if you wait for 500 hours or so, you reach steady state. In the steady state, below TG is higher. The nucleation rate is higher than above TG. All the maximum for homogeneous nucleation are below the laboratory TG. I'm telling about the DSC TG, you know. So, yes, you have to treat below TG for a longer time because you have more nuclei and much lower growth rate. So it has to go below TG, but very long. Another possibility is to add P2O5, which is a very known nucleating agent. But then you have a little bit of lithium phosphate formed, you know. In the end, you will not have the pure lithium disilicate phase in this particular case. But the thing is that the maxima are below TG. 30 degrees Celsius or so, like Helena. For the several systems, say you can go maybe 20, you do not have to go to the up maximum. Go 20 degrees below TG, but ask for your student to wait for half a year or so. Then she or he will have a very, very nice, yeah, below TG. Well, Professor Donald Newman, you know, I had this very famous professor, Donald Newman at MIT. He was the top guy in the glass field for years. You know, he wrote a famous book, Introduction to Ceramics, Kingery, Bowing, and Newman. That's Professor Newman. He's retired now for many years. But when he was a professor at MIT, he had a student that I met with a very long flower-shaped sample inside a gradient furnace. So you have a series of temperatures. That glass was a famous glass called albite. Albite glass is very, very, very difficult to crystallize. And he wanted to measure crystal growth rates. So he said, okay, Bill Doyle is this guy. Bill, you make a long bar-shaped sample. You build your gradient furnace. In the old days, you have to build your equipment. And left this glass inside for 4 years. He left the sample for 4 years. You know, he was doing some other thing, of course, doing his PhD. After 4 years, took the glass out, nothing happened. Then he discovered that he had to spray a powder of crystalline albite, you know, mineral albite, to trigger nucleation. And then he had crystal growth, and he measured crystal growth. So 4 years is good. It's a good human time scale, you know, for a PhD work.
This is dangerous subject because the guy can think that he has to wait to the crystallization, go away, go home.
Good. So I think we have more than enough today, and it's time now to relax a little bit. Like all classes, let's relax a little bit. Did you guys and ladies bring your delicacies, or you have to go to the hotel? Well, some of you have. So let's move downstairs, and those who need to go to the hotel, please rush. Go to the hotel. I think we have some vodka also. Yes, we had some vodka from Sweden. From Poland. From Poland. Oh, you're from Poland. You are working in Sweden, but you're from Poland. Okay. So let's try. Let's go downstairs. Thank you very much.
Perdeu, desformatou